to start asking is that is all we have to do just linear model, not linear relationship? Because as we all know, it's the world is not linear, so there are always other things. You want to have functions that can help you model such complicated relationship. So following the data science course.org resource, and if you don't know what that is, which which is almost not possible, because you should go to this site and get the slides from here if you want to follow alongside as I'm talking. So for today, the outline of today's class would be that we would return back to the peak demand prediction that I took 2 weeks ago, and would also talk about overfitting, generalization, and cross-validation. We'll talk about regularization. We'll talk about general not linear features. If time permits us, we'll talk about kernels and just a few slides on nonlinear classification. And so we'll start with the peak demand prediction. As we discussed 2 weeks ago, we this problem with the peak summer months temperature, which was what helped us to be able to build a linear regression model whereby we were able to fit a line through these data sets and we were able to make such prediction. But in truth, if you So let me share my screen. A brief interruption. If you wanted to fit a line through this data set, you can see that this is not going to be reasonable. Update our toolbox and add nonlinear regression to it. So what is nonlinear regression? What is it exactly? It's just as it is. We want something that is not linear. Anything that is not linear should be nonlinear. by logic. But anyway, to be much more concrete, just whenever we say we're doing something nonlinear, you can almost think about it as your something quadratic. Say you're like if you're linear, it means that I can your let me go back to like
Steady. Oh man.
TJ, I think the network is bad. Okay, I think she wants to change her internet, yeah? Let's just hold on for a while. Okay. Okay, while we are waiting for Teju to come back online, please, if you have ideas of projects that you want your group to work on, feel free to message me privately with and just state the idea, yeah? Just brief description. And let's see whether it's something that you guys can complete before or something we can consider, yeah? So just buzz me on Slack, anywhere, just buzz me anywhere. I would respond. So it's as a group. Then if you have if you want to work on personal projects, it's fine too. Yeah. But even if you are going to do personal projects, you should still do one with your group. The group project is compulsory, but personal projects are if you want to, yeah. Okay. I think Teju is back. Okay, she's not back yet. Okay, she's back.
I am here. It appears that I'm stuck with bad internet today. Forgive me.
Yeah.
Okay, so I'll go back to sharing my screen. Okay, great. As I was saying, I was just making an illustration of what linear means when we talk about linear and how we can relate it to non-linearity. I'll just make a quick drawing here. Not a drawing, just write a function, which is say we have f equals to 3x plus 2. This is a very common equation. It's in the format of you having mx plus b, and everyone knows that this is linear. This sort of equation will help you model any linear relationship. What does that mean? It means that your f, maybe I should not have used f, maybe I should have used y, but you get the gist. And same thing as to go back to our classical xy. So f, it does not matter what it's called. So, and I'm struggling with this too, but anyway, yes. Sure. Okay. Get there. We're almost there. Gosh. Oh my goodness. Okay. Yeah. So anyway,
Oh boy. TJ, are you still online? Okay. Okay, while we are waiting for her to come in. So even though I'm not with, let me see if I can put up the slides and continue from where she stopped. Give me 1 second. Sciencecurse.org. Hopefully. Okay, is she back? Let me share my screen. Or do I just do it? Okay, can you all see my screen? I think I would have to pause this. Okay, so let me pause. Let me pause the recording. Okay. Okay, you can start, TJ.
all right, thanks. So we need to have something that can help us model nonlinear relationship. So with that, we talked about cough, like how do we decide what polynomial it means? So I decided to pull up this graph.
Say you're back. Okay. We lost TJ again.
So, hello.
We lost you.
Can you hear me?
I think we lost you for a while.
Oh, okay. I am back now. You found me. So, as I was saying, there's nothing you do about like the previous curve. We could not fit a curve. All we could do was fit a line. But now we have a quadratic term, which is the square part now. So you can see that we can do much more interesting thing. We can fit any data that looks like this. So you can sort of like just have a feel of how this is happening. See? If that is not enough for you and you wanted to do more, like maybe your data set doesn't look like this, how about we increase it? Let's say another term had another quadrant, make it degree of 3, and then we make this, so this becomes x squared, and this becomes, say, cx, and then we have d. And we had another slider for D. You see what's happening here? Now you all of a sudden you have so many flexibility. You can change the different, think of this A, C, D as your thetas. So with different values of theta, you can sort of like do a lot more interesting things. It feels like a superpower, right? You can start fitting different kind of curves. So that's the thinking I want you to take back to talking about degrees, polynomial features. So if we say we want polynomial feature of degree 3, think about it as when we had ax cube plus bx squared. Think about it as like we have a data set that looks somewhat like this, and we think that this is what this kind of curve is what can help us fit our data set. I hope that was clearer a little bit. Moving on, how can we do such a thing in our current data set? We know we have one, at the moment we are working with just one feature, right, which is eye temperature. And so what we will do is that, why not, like, let's square it. Let's make this be a quadratic term instead of just a linear term. And that is what you can see here. We are now squaring eye temperature. Now we have two features. The third one, the one here, is the bias term, which also translates to, say, for example, the offset here, the D. It does not really matter much. And so we now have two features, right? The eye temperature square and then the eye temperature itself. And we can try to make prediction with this. But from the last class, we talked about a shortcut to ordinary least square regression, whereby you can mathematically find the minimum. So by, and if you're not familiar with the equation itself, I think we discussed something like this, where you have the solution for the least square regression being x transpose x, inverse of that, then x transpose y. You can almost see how this is possible. I'm going to try to give you a little bit of intuition. So coming back to our like our optimization objective, you know, we said we wanted to maximize we wanted to maximize a loss, right? And the loss, we said it's 1 over 2n, right? Some people put 2, some people don't put 2, but anyway, I'll just add this for illustration purpose. Or so we have from I equals to 1 to n, and this n is the number of data points that we have. And then we have our loss, right? Why our what's the loss called again? It's skipped my mind. anyway, y high minus our hypothesis hi, then we square that, mean squared error, yeah. So this is this equation here now is our error term that we are trying to optimize. So let's say for mathematical convenience this time around, we're not adding these two. So we're just having 1 over n summation from I equals to 1 to n, which is all your data point, y high, which is your true label, minus hi, which is your predicted label, then we square that. And so what happens now is that if we wanted to find, we want to maximize this term, right? How can we do that? We know that from our calculus, to maximize or minimize something, it means that you want to find the derivatives of that thing, and then you want to set it to 0 to find where wherever it's where that thing equals to 0 is the minimum you can ever be, or the maximum you can ever be. So we'll quickly do that here, and we want to. So we'll do like the error term, the theta. We know that the relationship between this theta comes from your h. So if you look at your h equals to theta transpose x. So this is the same thing. What I wrote here is the same thing as what Kenichi wrote before, which is just theta 0 plus theta 1 x1. So you can imagine that if you have more terms, say you have theta plus dot dot dot, say you have dot 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 then theta n x n. So you can have infinitely many features, and they'll all have their own parameters. To make it compact, we'll just use this notation of theta transpose x. And you can also, you can also write this this entire term here in a vector form, a much more compact way, which is the same thing as having, so you can have it as y minus h. So, and then this would be like this. So this is writing it in vector form. But let's expand it, because what we want to do is that we want to be able to get this equation here, the least square solution. And in order to do that, we just say that we said that the minimum would be wherever d theta equals to 0. So we want to find differentiate our error term with respect to theta, and we'll do that by saying that. So we'll come here. Let's rewrite this. It's 1 over n, right? Now we have y minus x theta square. So, and here I'm playing around with vectors and dimension right now. In this current, in my current notation, I'm assuming my dimension, what it's saying is that my x, I'm saying that my x is in dimension r n by d. So this is my assumption. So I'm saying that we have n rows and d columns, and my theta is dimension rd. So which means that I am able to do this mathematically. So if I multiply this together, I should get something with dimension of n. If this is not clear, you should definitely take a look at the previous videos. We've discussed some of these things, or I can also share more links to external resource that can help you understand matrix multiplication. So to have this now, we want the d of this, the theta, we want it to equals to 0. So what we will do, what we'll go on to do is that differentiating d theta of this, from high school calculus, we know that it will be 2 over n minus 2 over n, then x transpose, then you have your y minus x theta. And then we are setting this equals to 0. So we know, of course, like imagine if you had put, like if this was 1 over 2n, 2 would have cancelled 2 anyway, but this 2 is just a constant. It's also, if you divide all through by 2, it disappears before you know it, like minus 2 over n disappears. So let's just move, let's move here quick. And then the next thing, you can almost see that by going further, you're going to have something like x transpose y, right, minus x transpose x theta equals to 0. And if you simplify even further, you can find the solution for your least square. That is, I'm going to denote this by star, which is like the minimum, to be equals to x transpose x, the inverse of this, because by the time you take this term here and you want to divide it, you want to divide both sides by this term, it's the same thing as inversing. Then x transpose y. And this is just what we, like, this is just the proof. And instead of us doing the gradient descent step that we did to find our theta in the last classes, you can just write one line equation and you can get to your minimum without you trying to gradient descent it. Of course, this is because this is ordinary least square. It's not usually it's not as simple to just like find minimum. And also this also has comes with its own consequences in terms of, like, you can say that we have x transpose x. So it means that if you're, like, we are assuming independence here, because from our knowledge of linear algebra, if our features are dependent on one another, that means if they're linear dependent on one another, rather. So that means if you want to invert such a matrix, it will be non-invertible. So you would not be able to do something like this. You would need to add some other term that can help you deal with that. So like everything has its own pros and cons. So, and any questions so far? Was that clear? We haven't done more.
I'm sorry, I have a question.
Oh, okay. Go ahead, please.
Okay, so I'm seeing non-linear regression. Is this like a polynomial? When stuff doesn't fit into the linear space, we use a polynomial. When you say, oh, so non-linear situation, I don't really. Hello?
Yeah, I can hear you.
Yeah, so when you say non-linear regression, like you're trying to show a situation where linear regression doesn't work, right?
Actually, no. So if we come back to, it's all about your data. So let's say, for example, you have a data set and you understand how it's like the distribution of their data, and it looks like this. It looks like something like this. So you know that you can fit a linear regression, you can fit a line through this data set, and you'll be able to approximately, approximate the solution. You can, through using just linear regression, you're able to find solution for this sort of this sort of data set. So, but in the real sense, most of the time, your data set does not just have this linear relationship. It's almost impossible. You usually, in fact, the reason why we're able to visualize this is because we're just like looking at just one feature, right? Most of the time, you have your data set have a lot of features that it's almost impossible for you to be able to determine the relationship. It's almost impossible that the relationship between all the features with your label would have a linear relationship. So it's almost always non-linear. And this is an example of maybe if you decide to use all your like your temperature data, your temperature feature, instead of using just the summer time, where we extracted just the summer time from summer dates from the temperature. Now, if you wanted to use all of it, you can see that the relationship that it has with the peak demand is not linear. It does not follow a straight line. Does that make any sense to you?
Yeah, it's clear now. It's clear.
Okay, so because it does not follow a straight line, does that mean that we cannot build a model that would help us to predict peak demand?
Oh, yeah, we can, but not with linear regression anymore, right?
Exactly. We can, but not with linear, like we have to improve our hypothesis, our assumption. We can no longer use the linear regression. We need to be able to use something a little much more sophisticated. And here we are lucky, we understand how our curve looks like. I mean, even if we don't know what the curve looks like in the mathematical lingo, we can try as much curve as we can. We're just like, we're playing a game here. We're just fitting curves. We want to see which of the curve is able to help us like reduce our error and generalize. Also, don't forget that. So while we are trying to fit as much curve as possible, it's possible that you can find a curve that would exactly go through each of these data points. Like you can, like your curve can be so like finicky that it wants to have all the data point, but that is not your goal. You want something that, given a new data set that your model did not see while training, you're able to generalize. So you would not want something that fits exactly, and which is as we proceed through the class, you would understand what I mean by like fitting exactly. It's like Kenichi said, you have a higher degree polynomial. That's usually what we call it. Any other question before we proceed? Okay. So, and now that we understand how to prove this formula, which is good to know, it helps you better understand things and know what's going on. And so coming here, if we said that we wanted a polynomial feature of degree 2, like this is all we mean. We're just like fitting a quadratic line, sorry, not a line, a quadratic curve through the line, through this data set, which is a good approximation, wouldn't you agree? But maybe, just maybe, quadratic is not enough for this data set. Imagine the underlying distribution of your data. Maybe there are more data here. Maybe it goes like this. So it means that it looks something like this, not exactly like this. So if you add more data sets to this, your quadratic thing will not be a good, it would not be a good curve to give you the lowest possible error that you're looking for. So maybe we can do better. Maybe we could try polynomial of degree 3, right? See what it looks like. And then we come here, you can say, roughly, it looks roughly like maybe this is what it looks like. But we really don't know, because we don't know the underlying distribution of our data. And this is one of the things in like in this profession, what we're doing in machine learning. If you understood what the underlying distribution of your data is, it's very easy. You just like find you a curve that looks exactly like that, and you have a perfect model. But it's a lot of data set that you get. The word itself, you don't know what it is. You don't have underlying on like distribution. You don't know that it looks like a quadratic, or if you had more data, at first it might look linear, and then you have much and more data, then looked quadratic, and then you had more data, and then it's like it's all stochastic. I mean, that's what the world is, highly non-linear. So, and so coming back here, in order for, okay, this is just the code to help you be able to add enough degree. So, and you can see adding feature degree, polynomial feature of degree 4, you have something like this. And if you keep going degree 10, you have something like this. And if you keep going, say you're not satisfied, you had much more degree, you go as high as 50, you can see that you've now started to overdo things here. You're trying to fit each of the data points, and this is not good. And so this would naturally lead us to the problem of overfitting, underfitting. But before we go to do that, let's just talk about like I briefly mentioned something about your metrics being non-invertible, also known as singular. You have a singular metrics, and this happens usually when you have when you have linear dependency in your features. But there's also another thing. For you to better understand what this polynomial feature of degree 50 is doing, I don't think we are recording actually. Oh, we are. So for me to understand what this polynomial feature of degree 50 is doing, so imagine you have m examples in our data set, and you have n features, but this time around, the number of your feature exactly equals to the number of examples that you have. So n equals to m. So what this is telling you is that your feature matrix X would be m by n. In this sense, it's the same thing as m by m or n by n, which is simply a square matrix, right? And if you expand this formula, you realize that your solution would be X inverse Y, and your Y becomes X theta. What does that tell you? If you go back to your initial your initial equation that for your hypothesis, you remember that your equation is H equals to X theta, right? So now you have Y equals to H. So you fit your data exactly. But this does not mean that if you have new data point, you're able to generalize. But this is just explaining to you what it means by having higher features. Like if you have just as much, the number of your features is the same thing as the number of examples. It means that you're trying eventually in this present example that we're going through, you fit your data exactly. So another thing is that once you start dealing with a lot of features, there's a very, very big possibility that some of your features will depend on one another. You might like, of course, if you have infinitely many features, there's only so much you can do. Maybe one of your feature was like 2 times another feature. So and this breaks down. You're unable to, like, you know, of course, number one, you're unable to use this formula, and it's just if you're even using the normal gradient descent technique, it's a waste of time, really, because you're really not learning much from having a lot of features. They're not contributing any new information. So coming to, and sorry, at best, you should remove such features from your data set. And so coming to overfitting, generalization, and cross-validation. So how do you deal with this scenario? We have established the facts that we want to be able to model, we want our model to have higher complexity. We want to be able to fit better curves, but at the same time, we don't want to overfit our data. So what do we do? Maybe the natural thing to do would be, is there something that can help us know when our data is about to start overfitting, so we can stop and not add more term? Or is there something that can also help us penalize our model, like restrict it, even though we want high degree polynomial because it helps us increase our model complexity? At the same time, is it possible for us to be able to not restrict it in some sense? So which is the function of over general, what am I saying? The other part where you're restricting is the function of regularization. It helps you regularize. But before we come to regularization, we're going to talk about the problem of overfitting, generalization, and cross-validation. So, and I already discussed why we need our model to generalize, and the fact, and also discussed that as our model complexity grows, the trade-off we're having is that we have lower loss, but then our generalization starts. Let me use the mouse. We have lower loss, but our generalization starts to suffer. So moving to cross-validation, how we can be able to solve that problem is that, what if we don't train with all our data set? What if we hold out some data sets? So we gather a lot of data, but instead of just training with all the data sets and then just not knowing what happened, we got really low error. But does that mean that this can generalize? We don't know. So what if, apart from the test set that is outside of this whole conversation that you're not supposed to touch or look at, you're just supposed to, after you've trained your model, your test set is supposed to be the one to help you for sanity check, that tells you that, oh yes, this is not a good representation of your data set. But apart from the test set, which is somewhere that you're not looking at, the remaining training set, what if you can divide some part of it called validation or holdout, usually about 30% of your training set. So this validation data can help you understand when your model is starting to overfit, and you can stop at that point. So in layman terms, this means that it's helping you to adjust your hyperparameter. So your hyperparameter would be something like the degree of polynomial. It's something you're tuning yourself. You're making the decision. You're saying that I want degree 3, I want degree 5, I want degree 10. So your holdout data sets can be used to help you decide on what values is the most appropriate for your current data set. So moving on to the cross-validation code. Let me just quickly switch to the code itself here. Okay, yeah, so we discussed this. Now, yeah. Okay. It's the same thing. So this is just how you're able to do such partition. So you can play around with it on this code. Just download it on your, to your favorite tool, Jupyter Notebook, and then run it. But try to understand what this is doing. So the basic intuition is that you want a random permutation. This is just to help you with indexing. So you can think of this as, say you have index, let's say your data set is, you know, you have, I thought I was writing something. Okay, you have X, right? X1, X2. So this is like, then your table, you have 1, 2, 3 up to n. So imagine you want a certain percentage of this your data here. You want to hold some. One way you might first think about it is that, oh, what if I take 1 to somewhere around here? I use this part to train, and I use this part to validate my model. I mean, this is not bad thinking, but the problem you start to, the problem with this approach is that because you're you're not shuffling your data, it means that you might start to, I'm using the correct term here, but so this, you might not exactly, you might miss some point, say some benign cases, maybe some classes were more prominent in this part of your held out data that were not here. So and because you did not see those parts during training, you are unable to train a good model that would help you solve that problem. So the way to go usually is for you to shuffle. Instead of taking just one bunch of this, you want to randomize this index 1 through n. So that you have something like 17, 38. You get the idea. And so once you have this now, you can now, that's the job of your palm here. It's helping you to do this sort of like permutation, like run shuffling thing. And then you can now have your index, like a train index, and then you have a cross validation index. And the next thing you want to do is that just partition it based on that, which is what you have here. So you're saying that you're locating your index of train, and then that would be your training set. This is your training level, and this is your training data set. I hope that is understood. So once you have that, the next thing you want to do, I mean, I'm skipping through a lot of this thing because we've discussed it in previous classes. We already discussed what it means to normalize your features, which is something that's going on here. And so this is your error term. So you can see we're like this formula here is just what it is 1 over 2n summation blah blah blah. You get the gist. We've discussed this times without number. So this is simply what's happening here, and you want to have this 1 over some 1 over y minus your Y label minus your predicted, which is what you have here. See, this is your predicted, and this is your true label. So now that we have the error of cross-validation and your error of train, you can now understand, if you plot your graph, you can see when your model starts to misbehave very, very quickly. And an example is that if you look at this chart here, this curve here, so imagine you had so this is, let's say, imagine this is I'm pointing at something, but I'm sure you cannot see it. You can see my mouse, right?
Yes, we can.
Oh, great. Sorry, I was thinking you can't see it. That was my dilemma. Okay, anyway, so imagine this is your validation set that you use as a generalization. A natural thing to do is that you're supposed to like maybe stop training around this part when it's about to start deviating. So, and that's just the basic idea of having like your training set and your validation set. And you can see that the validation set, like I mentioned, it helps you to determine your hyperparameters. And this is illustration of cross-validation. Imagine like this X cross-validation data set that we have here as the XX, the green part, and your training set as the blue part. You can see that you have a good mix. It's not like your cross-validation set is like one part of this curve, and then your training set is this part of this curve. There's no way your model can be able to learn about this part if it has not seen it before. So it won't be able to do it. That's why you have to do the shuffling thing so that you have good representation of all your classes. If you're dealing with classification, it should be like all your classes should have equal distribution, like equal numbers as you have in your training set. So and this is also visual, like as your polynomial degree increases, your average loss, you can see, of course you can't see very well now because this is just to show you how crazy it becomes on the older data set. But if we try to zoom in, let's say we zoom in at 10 to the negative 1, 10 raised to the power minus 1. So you can better see that your training set the loss continues to go down. It's now linear. We notice that we're using a log scale. That's why it looks like this. But your held out data set is increasing. A natural thing for you to think about is that what if I stop training, maybe say around 6 polynomial degree, not much is changing anyways anymore. So if you stopped around this 6, you still like get a really good representation. So any questions so far?
Hi, Teju.
Yes, I can hear you, Obira.
Okay, so we've seen what happens when we put in so many features and it's overfit. So what if we do not like the efficiency we've gotten thus far? How do we make the model better since we cannot put in more features when we cannot put in more features? I don't know if you get my question. How do we improve the efficiency of the model, the accuracy of the model when we've come to that point?
I'm not sure I get your question.
Okay,
correctly.
so okay, let me try again. So you showed the training set, and you also showed the cross-validation set. Now, what if with the training set, we have maybe we want 80% efficiency in predicting values, in predicting things, and then with the training set we have maybe gotten to 60%, we've not gotten there to 80% yet. And then the cross-validation set also hasn't gotten to the 80%, certainly, since the training set hasn't gotten there. How do we improve the model? How do we try to increase the efficiency as we cannot, so that we won't overfit, but yet improve the efficiency?
Yeah, I get what you're saying, but so maybe you've tried you've had you've added more column, right? You've been able to do a higher degree of polynomial. Or a natural way to think about it is that maybe your current feature is just not enough to be able to give you good answers on your data. So why don't you collect much more informative feature? Or why don't you collect your first thinking would be you need to find more features that can help you better predict well. While maybe if you also do a lot of manipulation, say you do degree polynomial on all other features, and then you combine it together, and then you continue to mix those features together, by the time you retrain, perhaps your model can find good good fits into your data.
Okay, thank you very much.
So, but if you're
okay.
What?
Sorry, please go on. Please.
No, go ahead.
Okay, thank you. I understand what you said. Will adding more examples also help? Maybe looking for more examples.
Yeah, that was going to be my second suggestion. Say you are satisfied by your features, or you just cannot find more features. I'm talking about like the classical machine learning scenario whereby you extract features by yourself. We know that in like the deep learning techniques, you don't have to worry about features by yourself like anymore like you do in classical machine learning. In this scenario, what do you do exactly? You might want to increase the number of your data set. Maybe it's just too small. Maybe you need to add more data so your model can learn from more data point, and it can understand what the distribution looks like by having more data.
Thank you very much.
Okay. Any other question? Okay, so coming to k-fold cross-validation, you can almost see that the problem with just having, like just leaving out some parts, like a partition for your validation set, is that what happens if you have really small data and like you can afford to leave 30% of that data, because it means that when you're training, you're not training with enough data sets, and you're not expected to find good model that can be able to give you good accuracy that you want. So another trick, another technique rather, that you might consider is something called k-fold cross-validation. And what that means simply is that it's the same idea of having train and then holding out some part, but this time around you bucket your entire training set into folds. Say you have 5 folds. So what you do is that you use 4 folds to train and 1 fold to validate. So, and then you do this 5 times. So like at every point you're using different folds, you're combining different folds to train. So let's say, for example, you build the first model, you used fold 1, fold 2, up to fold 4 to train, and you use fold 5 to evaluate. And then you do it again. Maybe you use fold 1, fold 5, fold 3 to train. Then a fold 3, fold 4 to train, then you use fold 2 to evaluate, and then you repeat that k times, like as much k as you're using, and what you eventually do is that you report the average error over all these held out folds. So and this works a lot in practice, actually, like especially when you don't have you just cannot afford to leave leave a lot of partition, and especially if your data set is small. If this sort of technique also transfers to, I mean, when we're talking about things like ensembling, where you build different models and then you average their their results, and then you get a bigger, like a better model, like a model with higher performance, because it takes the best of both worlds and it averages them. So, but maybe later in the future lessons, we might touch on that. Another variant of this cross-validation is something called leave one out cross-validation. This is same technique as before, but the difference now is that instead of using a fold, like a k fold, to cross-validate, now you'll be each fold is a single example. Imagine one single example like 1, 2, 3, like one of it is a fold, and then you train with all other example, then you cross-validate with just one example. So that's another technique. Like you can try out different things, see what work, and what works and what does not work. And it says here there's also another one called stratified cross-validation. I think this is my favorite, because this does not just this ensures that whatever folds you're having has equal representation. So it goes back to what I mentioned before when we did the permutation thing for the cross-validation, where I said that you need to make sure that you have equal representation of your data sets of each of your data sets in each of your training buckets, and your validation buckets. So the stratified cross-validation ensures that approximately equal percentage of positive and negative examples or any other features in each fold. And there's a warning here that k-fold cross-validation is not always better. And an example is something that if you have a data set that depends on time, if you do the shuffling, it's just. So what you mean what I mean by saying that it does depends on time, it's like what happens in the future it depends on the patterns of what has happened in the past. So you want to make sure to be able to understand the pattern as it is, not shuffle it up and then break the old pattern. So in such case, your k-fold cross-validation might not be a better strategy to go. So and that concludes the part on cross-validation, generalization, overfitting. Do you have any question? Okay. I can see a chat. No question. Great. So so let's move to regularization. Can someone tell me what regularization means? We've discussed this in previous classes, so. Anyone?
Okay, can I try?
Please go ahead.
Okay, so I think regularization is the means we handle overfitting by. So what I'm trying to say is that um, just as I remember Kenneth gave an instance where a child was being taught what a blue duplex is and what a red bungalow is, something like that, and that because the child was just focused on those two, he was sort of overfitted to know just those two kind of houses. But what regularization does is that it tries to keep us from being too focused on the particular things that have been shown to us. It helps us to generalize better. That's how it is in my mind. Thank you.
Thank you so much. Yeah, that's a good explanation. So basically, it still addresses the fundamental problem that we discussed. How do we not overfit? How do we build a model that is able to generalize to like a test set to a data point that it has never seen before? And one technique that we previously discussed is the idea of having like held out data sets to help you control, like choose your hyperparameter and everything. But you can also use regularization technique. And so the idea of regularization is that let me quickly skip. Okay, it's not here. Okay, yeah. So let's come here. I think it's here. Well, hello. Can you all still see my screen?
Yes.
Okay, I had to refresh real quick. And so one moment, I just want to show you something which I think would be interesting in helping you understand why regularization is so useful. So when you fitted about 100-degree polynomial as, say, this polynomial that was fitted here, look at, let's sort of like let's dig deep into the theta. You can see your theta parameter has really high values. It's going as high as hundreds of thousands. So it means that as you increase your model complexity, your theta value suffers. It increases, like it needs, like it has more weight. Your weight increases, and then that's why you're able to do this sort of thing that you have right here. That's not the best explanation, but that's what I can come up with right now. So so the alternative way would be for you to penalize this weight. Like, what I mean by penalizing is that you want it to be as small as possible. So once you do this, it means that you need a term that would directly influence all these your theta values. And that's just basically what we do in regularization. So the regularized loss minimization problem looks like this. You can see that you now have a term called regularization term, which is directly influencing your parameters here. So your theta 1 to theta n, you're going to ignore theta 0, which is the bias, but like you're only trying to penalize your other weights to keep the weights small. So, like, does that make any sense to you? I think it should. We haven't really discussed much, but please feel free to put it on chat if it does not make sense. And so what this means is that you're varying your lambda from, say, 0 to infinity. If you say your lambda is 0, it means that you want your theta to be like you're polynomizing it. I'm sorry, if your lambda is 0, it means you're not penalizing. So if lambda is 0 here, you can see this side, this term becomes 0. So it means that you're not applying any penalization. But if you increase your lambda to say infinity, you're heavily penalizing your model, and you end up with a model. If you penalize all your term, it means that you end up with a model that is only like with only the offsets, because the other terms are 0. And so like if we dig deep into what the ordinary least square regression solution would look like, it's pretty much the same thing. You just minimize this term now, and then you set it to 0, and you realize that now all the changes that happen to your solution is just that you now have this term, which is the lambda term. And this I is just your identity, meaning that your lambda is on the column, instead of you just having one lambda, because this is a compact vector representation. So it means your lambda high is a matrix, and your high is your identity matrix. So okay. So looking at, let's do some visualization. If you have a degree polynomial fit of 50, like we said, and then you make your, like if your lambda equals to 1, you can see that you quickly move from a heavy, like a really heavy curve, like trying to overfitted model, to something that looks reasonable. So now you're penalizing your model with a lambda parameter of 1. And if you look at the cross-validation loss by regularization, you can see here, that as you increase your regularization term, your model starts, your average square loss starts to seem like it's generalizing. And then as you increase, your loss increases. Because you remember what I said, by you increasing your regularization term to infinity, it means that you're penalizing all your parameters. And if you want to think about it much more deeply, it means you have, let's say, you remember our equation is theta 0 plus theta 1 x1, then you go to theta n x n. So if you now analyze, say you have your lambda tends towards infinity, so it means that you want all this theta 1 to theta n to be 0, and what you're left with is just your bias term. So definitely your bias term is not enough to give you, to model your it's not enough to model the behavior in your data set. It means that you would lose, your loss increases. So you get back to square one. And so this curve can help you understand that an ideal regularization term would be, say, 10 to the -3 to say 10 to 1. So you want to, for this particular problem. And this is just showing you by zooming in that, like, if you continue like that, your average square loss starts to increase. And here's a question for you. Suppose you run linear regression with polynomial features, and some initial guess for D, which is the degree of polynomial, and lambda, which is the regularization term, you find that your validation loss is much higher than your training loss. Which actions might be beneficial to take? You can unmute if you want to speak. I'm going to assume that you're still reading the question, so I'll allow you to take your time, give you 5 minutes to think about it. Okay, I wasn't counting, so I'm sure that was not 5 minutes. So anyone? Which action might be beneficial?
Hello.
Go ahead, please.
Okay, so I will decrease the, that is, decrease of the order of our nonlinear equation. Hopefully that will work.
Okay.
Maybe the reason why the validation loss was much higher was because I overfitted, and
Yes, definitely.
so I'll reduce the. Okay, then as for lambda, I'm not so sure what I should do to lambda. Yeah. Thank you.
All right, thank you. That's a really, really reasonable way to think about it. Your validation loss is much higher. The first thing that should come, and you know you're using degree of polynomial. So to what's that term where you try to get more features? Yeah, it's my mind again. So you know you're using degree of polynomial to increase the number of your features in your data set. So the natural thing for you to think about is that, what if I decrease this degree? Maybe the degree was too much. And another thing in terms that you must think about is that, okay, what if I don't want to decrease the degree of my polynomial, but perhaps I should increase my regularization term. So if at the moment I was not using any regularization, it was 0. So why not add regularization to penalize this the parameters that are becoming bigger and bigger? So I could also increase my regularization term. Does that make any sense?
Yes, it does. It does. Thank you.
All right, great. So, Fortune, I saw your chart. Yeah, option C is definitely is something you should do. So that concludes the part of regularization. And any questions so far? Okay, we have a few more minutes to go. So let's see if we can get to general nonlinear features itself. So this part gives you much more intuition and how we can generate more nonlinear features. And let's say, for example, we have more than one, at the moment, we're just using one feature, which is eye temperature. But in real life, in real cases, you have more than one features, right? You probably have, we know from last class, we had eye temperature. We also had is weekday as a feature. So we might want to also combine that and then have our feature table. And so this is trying to help you distinguish. You can see here, we previously described polynomial features for a single raw input, X. But if our raw input itself is multivariate, so if what we're dealing with is not univariate linear regression, but we're dealing with multivariate, how do we define these polynomial features? So natural way to think about it is that, okay, let's say we are now going to start using a different notation, right? We use X to denote that your original, your multivariate features, and then we use phi to denote all your features, including the ones that you generated from this, your multivariate features. So don't get, I understand that notations can be a mess in machine learning, but like, as long as you understand what it's trying to tell you, you're fine. So we would say that phi is a function of your features, of your multivariate features. And this is just an example. So example, for eye temperature, you have X as eye temperature, and then you have phi as your eye temperature square, your eye temperature, and the bias. So let's say if you had X as eye temperature, comma, is weekday, then that's another, so that your phi would be something like your X, which would have eye temperature and weekday, and maybe you want to start using your X1. Your X1 is eye temperature and weekday, and your X2, sorry, apologies. Your X1 is eye temperature, your X2 is weekday. So if you wanted to like do your higher degree of polynomial and you want it to be on your X1, so you can have like X1 squared, X1 cube, X1 quadrupled. So you can have all those, and you can also have X2 squared, X2 cube. You can also have that. So, but in this case, it will not make sense to have X2 cube, because I just said that my X2 is weekday, and its weekday is either true or false, which is 1 or 0. Squaring 1 makes no sense. Square rooting 1 is, I mean, you can square root of 1 is what? Negative I. Anyway, so is it negative I? Yes, it is, right? No. Square root of negative 1 is I, right? Square root of 1 is, it's now that I'm thinking about it, what's the square root of 1?
Okay, square root of 1 is 1. I think what you're referring to is square root of negative.
Yeah, square root of negative 1 is I, right? And square root of 1 is 1, right? So it makes no sense for you to say you want to increase the features by square rooting 1, or like square 1, or square 0, or square rooting 0. So there's no operation that you want to make on such a feature. So moving on to this. So this is what your new vector would look like. You would have X, which is in the range of K. Like you have X, the dimension of X is K, and then you have phi, which is dimension K times the degree. This is polynomial degree, K times the number of degrees, 10 plus 1. So in this sense, if you have one feature, like one raw input, and you have degree of 3, so what will be your phi? Did you get the question? Let's say you have your K, your K is 1, that means you have one feature. And then your polynomial degree is 5. What would be the dimension of your phi?
Okay, so it should be 5 by 1, a 5 element vector.
Yeah. So that.
Oh, sorry, 6. 6. Sorry, 6
Yeah,
plus 1.
exactly. Yeah. So that would be 5 times 1 plus 1, which is 6, right? And you know that this plus 1 comes from this higher stem, right?
Okay.
Yeah, great. So, and but this, what we just have here is not like it's not 100% correct, because it means that we're ignoring the terms, like the cross terms. For example, you could have x1 times x2 square. You could have x3 times x1 cube times x2 quadruple. It can get really complicated all too quickly when you're trying to like cross the terms and everything. So, and you should start asking the question that what's the, as you increase the complexity, like what's the um what's the word, like big organization, what's the space and like space and time complexity. So that's a natural question. Like if you have a lot of features, like how long would it take you for you to train, or how long does it, like how much memory this consume? So those are the questions that should start like forming in your mind. Anyway, in general, this is the formula. And what this is saying is really, it's really simple. So it's just like, instead of having k plus 1 k times t, it's saying that you have your phi will be dimension in which you have k plus 1 choose t. So this is just a combination. You can think of it as being your normal combination that you're familiar with. You have k plus 1 elements. Out of k plus 1 elements, you want to choose k plus t elements, rather, you want to choose this. So it's k plus t choose k. So this would be your dimension for this. And because you have to deal with all the cross terms as well. And so moving on, in order for you to and the code has been nicely written for you. I mean, if you wanted to find the cross term, you can just like use this iterative tool from Python to get the combination with replacement, and then you use it to generate your polynomial with the cross term with it. I encourage you to check the notebook after the class and run it if you're yet to run it. So, and that naturally leads us to questions like, is the only way for us to increase our feature, like to do, such data augmentation that we are doing right now, which is like we are increasing the number of features. You might ask that, is the only way to do it by increasing the order of polynomial? Is there any other technique to do it? And that's the question radial basis function is here to answer. It's like the answer is that no, there's not just one technique to do that. So you could as well also create more features using radial basis functions. And radial basis functions, like if you're familiar with Gaussian curves, you see that like it looks just like Gaussian without the, it is just like Gaussian but without the standardized normalizing term, which is 1 over square root of 2 pi sigma square. So if you had that, and the other thing is that your radial basis function is between 0, your y part, you have to normalize your data to be between 0 and 1, because that's usually what it's expecting. So you can see that it's written here that you need to normalize your column to be the same range. And the reason why this is important is because intuitively, the reason why we're doing this is that we're trying to find representation for our data in the embedding space. As you think more about this problem, you understand why we are going through all this trouble to begin with. So what your radial basis function wants to do is that you come here. Let me see if I can make a quick drawing. Is it? No, it's not. Okay. So let's say you have two features, right? So and each, we have x1 and x2. So what your radial basis function is saying is that we'll need to be able to, for each data, like each data point, there are different data points here. Let's say this. For each of these data points, we need to find a representation that is good enough in the embedded space, such that if you take this data point here, that representation is enough to tell you where the data set lies and help you be able to model it in an interesting way. So if I go back to showing you some curve, okay, maybe not here. Okay, so let's come here. Radial. Okay, yeah, so you can see this is what the radial basis function looks like. It just looks like a normal Gaussian, but it's not standardized. It's losing some of the Gaussian formula, and you can see it's between, right now it's between 0 and 1. And if you have a lot of radius, it means that let's say you have more than, you want to generate say 10 more features. So that means you want to fit 10 radial basis functions. And this is the idea. So it's like, imagine this is what you're doing. You're fitting a lot of these functions, and you want to combine them in such a way that they help you give good representation of your data. And so it means that each of these functions would have their own mean, which is the mu, we would have their own mu and their own sigma. And sigma here is just the bandwidth. It's just how far is it, like this, it determines this bandwidth, and it also help you determine how close each of these curves should be to one another. So what this is eventually going to say, let's say, coming back to our diagram here, let's say, for example, instead of these dots that I put here, instead of them being the data points, imagine that they are means, like different means. So we have x1 and x2. We sort of like grid our embedding space. So we have different means. Just look at this graph. Okay, so let's say this is one mean, this is another mean, right? Because if you look at this, it's the center of the curve. This is another mean, which is the center of the curve. So let's say you have different means, right? Which is scaled differently. And you now have a new data point that is here. So what's your radial basis function we want to do is that it wants to find the distance between this, your new data points, and all the means. So inevitably, what you end up doing, so that's why it's important for you to normalize, because it's sort of like it's finding the distance in the space. And if your features have different, if they're not properly scaled, the distance can be different. Like it will not make sense anymore. You cannot eat your chest and say that no, I'm certain this is a good distance between X and Y. So coming back here, you can see that you have the distance between your X variable and the mean, meaning like each of your data points and the mean. And the good catch about radial basis function is that because you're doing this exponential thing, and it means that as the distance increases, majority of this huge distance will be 0. And what that leaves you with is that you only have the distance, you only have something when the mean is when the data points you're currently observing is close to a mean, while most of the others would be 0. So it means that a lot of the features are centered, like they're like in the middle. It's not you just like having different radial basis functions. Not everything is useful at the end of the day. I know some of what I'm saying might look abstract or makes no sense. I would encourage you to watch the video from the lecture to better understand this. These are really good concepts to understand, because it helps you understand a lot of how the behavior of these functions and why sometimes you obsess about them. It's because they can be really powerful when you combine them in an interesting way. So, and let me just clear this dry. Let me see what else we're supposed to talk about here. So that's okay. Yeah. So coming here now, you can, like I already explained this. You just slot in the like the formula, and then this is like you get all this. So and this is the code. So there's a question like, what do you think the complexity of computing these features would be? Anyone? You can just guess if you don't know. What do you think it should be? What do you think the complexity would be?
As a guess, I think it would be number 1, the big O of MMP, just a guess, because I since they are n-dimensional inputs and then
Yes.
M examples and then P centers,
Yeah.
so it will calculate it for each case, and that just equates to multiplying N times M times P.
Exactly.
The explanation. Thank you.
Yeah, so that's it. Your complexity is linear. It's just n times p. You're not going with all the things you're doing. You're still well within the linear regime, which is good. I mean, it's not the best, but it's better than like quadratic or polynomial complexity. So yeah, this is just like some extra. I think, okay, we still have about 15 more minutes. Let's see what else we need to discuss. very useful for you to know. So these are just some extra term, which is yeah, it's just difficult. You can read this after the class. And yeah, I'm not sure we would have enough time to to go over kernels today. Like those are another thing entirely. So let's use the remaining 15 minutes for questions. Any questions so far? Hello, any question? Okay, so if no questions, then maybe I should ask question. So can someone give me like a brief summary of all that we discussed today? Just from what you understood so far. It will help me gauge how much we understand and what else we need to discuss.
Okay, so I try. We
Thank
looked at
you.
non-linear regression. We saw that it's not in every case we can just put a straight line through our graph, through what we are trying to predict. A straight line doesn't always work. And so sometimes we have to make the equation more complex. And so that's what gave rise to the nonlinear equation. I noticed we saw that sometimes we have to increase the degrees, that's putting polynomials in some instances and just to better fit the curve we have. Okay, so after that, we consider the problem of overfitting. That yes, it's possible you want to make a curve that goes through the points and all that, but it's also very dangerous to overfit. That overfitting will make what you create, the model you create, not to generalize better. That is in, well, for cases that were not considered in your training model. And so we consider overfitting, and we saw that one way to eradicate or to minimize overfitting is to reduce the degree of the polynomial. And another way is regularization. Another way of, of tackling overfitting is by regularization, compensating, subtracting something from all the parameters. And so it helps. And then we looked at, I think it's called radial, something radial. We saw that there are some cases where you should combine parameters together. I hope I'm getting the word. For example, when you're creating new features, sometimes you may want to create new features for your set. And so you may have to combine parameters, two different kinds, maybe x1 and x2 together, where x1 is a feature and x2 is another feature. And so I think that's what gave rise to the radial RBF something that we looked at. Sorry, I didn't get the full name. The radial bias or something.
Radial basis function.
Okay, thank you. So it gave rise to the radial basis function. From what I understood, the radial basis function is a way to do the cross feature relationship so that you will build a better model. Okay, so that
Not quite.
Okay.
Just one correction. It's not. You can also do cross features with polynomial. It's not like radial basis function. Just think about it as another way for you to create more features. Another technique aside just the polynomial.
Okay, okay. Thank you very much. So that's just a brief rundown of what I need to do. Thank you.
Thank you so much. That was a really good breakdown. Any other person want to say something? This is a good way for you to also test. There's no right, wrong answer, but please note that we're recording this class and it's always available on YouTube. So in case you don't want your identity revealed via your voice or your name, you might not want to speak. You might put it on chat. Would any other person like to? Chidimapa, oh, I just mentioned your name. I hope you don't mind. Another person. Okay. So that concludes today's class. And but I would allow Kenichi to wrap things up in case he has something to say. Thank you for coming and for your attention. So next class we'll discuss a bit about kernels and wrap this chapter itself up. There's not much to go. It's just it's a lot to take in as a first time. You need to digest this part, and most likely you should reread just to understand everything we discussed today. And next week, I think it's on probability. So I'm not sure if we would skip that part or if we should go over it, if it's useful to go over it, but we'll let you know. Again, as a final reminder, we are following this course. Please go over these slides and the notes. They're really easy. And this is where we heard. We should talk about basics of probability, and then we talk about naive Bayes. So we still have a long way to go. I'm not sure how much we'll be able to cover in the next few weeks. And can you please talk about the idea of projects? We should form groups. Thank you.
Okay, thank you, Teju. Yeah. So for the projects, I already studied earlier. Yeah, every cohort we usually have projects being completed by the students, and it's usually completed as a group. Already, the class has been divided into groups, right? I don't know how active each of the groups are, but I know at least one person in each of the group is active. So I'll be sending out a message, yeah, to each of the group leaders to know how the activity in the group has been so far. So for the project, I'm open to taking in project proposals from either the group or from individuals. Yeah, but if a group doesn't have a project that they will want to work on, I can also propose projects that they can work on. Yeah, myself or Teju will also think of projects that you guys can work on. But the idea is that we want each of the groups to work on different projects that will be presented. So it's not just to complete a project and then the project is just there. We'll also see to it that these projects are publicized, that the public knows about this project, and it's part of the things that go into our Medium articles for the cohort. So it's something we should all take serious. Yeah. For the proposals, I've already started getting proposals from some of the participants of this cohort. Yeah. So, but I'm still open to collect proposals, and we should try as much as possible to do it as quick as possible so that we'll all start something, yeah, and finish in due time, right? So I think that's all about projects. Then the other thing I would want to say is that for you to be able to actually work on these projects, it means you should at least up to the class, today's class, you should have some understanding of everything that has been done, yeah? And I understand that it won't be so easy to just start a project when you've not done some things with regards this class. That's why I kind of emphasize that everyone should go through the codes that I put on the GitHub page. I don't know how many people have gone through it, but I know that for those who have gone through it, they kind of have a very good understanding of at least linear regression. Yeah. So another thing I can try and do is to probably put up a practice machine learning project on Kaggle or Zindi. I don't know if how possible it to be on Zindi, but any of the two platforms where each person, not as a group this time around, because the learning is on an individual, everybody is learning for himself, yeah? So I could try and put up a challenge on Kaggle or Zindi for everyone to participate on, just for you all to kind of get familiar with data processing, machine learning, and the rest of it, yeah? So if I'm going to do that, it's going to be sometime within this week, yeah? And I encourage every one of you to participate, yeah. I think that's all for now. Oteju, do you have anything you would want to say? Can leave the chat.
No, someone said that please help use real life examples to enable us to relate more. So I'm not sure if that's
okay. Do you mean for the project or for?
Yeah, that's what I'm not sure, because most of what we discussed today for the class, apart from the mathematical part, we were talking about like grids, temperature, which is like real life example. But so I'm wondering if the person can clarify.
Okay, well, if it's for the project, yeah, it's definitely going to be from a real life example. And then even for the class, yeah, it's real life data that was used for the class, at least a peak load analysis. Real life example.
We even went through, like, we did the data, we collected the data, we cleaned the data.
Exactly. So it's not like we just got one random. I had to go through their site to go get the data. So it's a process. It's not even though we did it for specific years, you can also do it up to this year. Unfortunately, we don't have such access to such data in Nigeria, as if we would have done it for Nigeria, right?
Okay. Feedback is also welcome. Please don't hesitate to share your opinion. Maybe with me, with KHA publicly, it's okay. So, thank you.
Okay, thank you, guys.
Thank you. Thank you.
Yeah. I guess that's all for now. Have a great week, guys.
Yeah, thank you.
Yeah.